quantum sensing, various ways of sensing you people have come across, and also mainly the sensing means measuring something to accurate level so that we can have a better insights. And especially when it comes to quantum sensing, which we are going to measure is a very sensitive quantities. So while measuring, there may be a problem with the destruction of the system, like a demolition of the system. When it comes to tiny systems, that's where we are going to use quantum computing or quantum measurements. You had gone through the various ways of measuring, why the measurement is having some standard limits, and why measures are going to induce some disturbance in the system. All those things you might have come across, right? So when it comes to measuring, you can measure using a light, that is light sensing using. You might have gone through various ways lights could be understood just like any quantum material, like say electrons and photons, as electrons and protons and so on. And then you might have gone through sensing using Lego and quantum dots, right? Using laser systems, especially atomic clocks, right? Yeah. So, in today's session, which we are going to do is, we are going to talk about something called quantum gravimetry, followed by atomic magnetometers. Okay. So, we'll start the session straight away. Fine. Okay. Right. You are seeing this, the PPT, which I'm sharing right now. Okay. So, as usual, what we do is we'll go through the slides. Wherever we need some kind of a description using some notes, we'll do that. Okay, some blackboard notes, we'll do that. Okay, as title says, quantum gravimetry and gravity gradiometers. Okay, so which is something to do with the measurement of gravity, you see. Fine. So for that, we can use various ways. We can use gravitational force of attraction from on the objects which are above the earth, on the earth towards the center of earth. We can measure it, right? That is how we are going to measure our weight. Fine. So especially which we can do for particular cases. If I had to answer a question, why do I have to measure the gravity? One thing is measure the gravity, and the next thing is why I had to measure precisely. See, gravity we measure something like G is equal to 9.8 meter per second square. You see, okay, which is acceleration due to gravity. If I have any object placed on the above the earth, it just falls down, or I might say accelerate towards the center of earth. If it hits the surface, it stops on the surface. If the object is so heavy, in that case, probably it will even penetrate to the surface of the earth to some extent. You see? On the other hand, if I go to a surface where the surface is very dilute, not thick, solid surface, for example, a mud. Okay. If I drop something, it sinks through the mud because the gravity and the action of force on the object is more. That force is not nullified or countered by the repulsion force, some kind of a Beyond's force exerted by the surface of the mud surface. Okay, when it comes to water surface, let's say a water body, you go to a lake, you drop something, obviously it sinks through the water and goes stands at the bottom where the surface of solid surface would stop that to go beyond the solid surface. Okay, so that is what acceleration due to gravity. When I leave something from certain height, initially it's traveling towards that this little low velocity wise. As it comes near and near to the surface of that, it accelerates. That is what we call acceleration due to gravity. Okay, how much acceleration happens for every, right, for 9.8 meter per second, right? So let's say when I see at a given second there is some kind of a velocity, after some time if I see like 1 second after, the velocity is accelerated, means varied by quantity of 9.8 meter per second. That is the amount of variation of velocity happens. So that is what we talk about acceleration due to gravity. By the time it hits the surface of the earth, what is the gravity? It will be 9.8. Okay, fine. So the question is, why should I measure with that? See, even there are other later significant figures after 8 in 9.8. We are not going to specify in general when it comes to, I'm sorry, when it comes to some applications where we need the later significant figures also, that is where we are going to mention, and that is where we are going to take the most accurate value. Okay, where exactly this is required, that is the precise wise, I have listed here. There is something called surface resource detection. Okay, below the surface on the earth there is a lot of minerals, oils, right? So like there are lot of minerals we may need. Okay, not only below the earth we search for water, beyond that we search for minerals also, and we do search for crude oil, right? And some kind of water bodies, aquifers, that is we keep searching for our day-to-day life or even beyond. Okay, so if you are searching something, you find something at some point, it should not miss by few, let's say a few centimeters or at the most few meters. Otherwise you are digging to acquire or extract that kind of a minerals. If it misses by meter, it's you are going to miss a lot of resource, you are going to waste a lot of resource. Okay, and for example, water bodies sometimes they expand to a greater distance. In that case, here and there, few 1 or 2 meters is fine, but if it misses by a lot, then you are going to miss the water body. Okay, fine. So the surface resource dissection involves a gravity. Okay, basically depending on the minerals below the earth surface, there may be change in the gravity. How much change in the gravity is happening, that will be an indication of a kind of a crude oil or a water below the surface of the earth. Okay, and next thing is when it comes to navigation. Well, let's say currently we navigate through our uh, uh, navigate through our satellites. We send a signal to satellite. Satellite figures out where exactly you are located. According to your location, the GPS, like a satellite, will send what is the next point. Okay, we do use Google Maps using based on the GPS. But when it comes to tunnels, below the tunnels, probably you may not receive signal from the satellites. Okay, and even sometimes underwater the signals of the satellite may not be able to penetrate through the water. So that is where the GPS may fail. Okay, right? So for example, in the oceans we have submarines, defense submarines, right? When they fire, they call torpedoes. When they fire, the torpedoes has to travel certain distance and hit some other enemy submarines or sometime even other ships. Okay, so in that case, you may not be able to rely on the GPS. That is where you should rely on the location base and the location of the object and the location of the torpedo at a given instant of time. It do like experiences some gravity. Based on the gravity, it has to be located. So that is where you can do the navigation without GPS if you happen to know how to measure the gravity to a very great accuracy. Okay, so that is required in the case of defense. So we need to measure gravity to a very good extent. Okay, the next thing is the seismic monitoring. For example, earthquake, right? The tectonic plates actually they rub each other and they may let's keep keep adding the strain as they come close. After some time, when the strain increases, one is probably another, they will try to readjust the tectonic plates. That is the time earthquake happens, right? The tsunamis do happen. So even before happening these things, there will be a change in the gravity as the strain acquires between the tectonic plates. So there may be change in the gravity at some level at later significant figures. If you are able to know that, measure them, then you can predict the earthquake. I think little advanced, not completely in advance, so we can at least plan something for that earthquake and tsunamis, right? Okay, and the next thing is fundamental physics. See, everything inside an atom, just like solar system, electrons are revolving around the nucleus. They are actually put inside the atom due to that, like a gravity or attraction between nucleus and the electrons, the Coulombic force of attraction. Okay, that is fine, understood. When it comes to nucleus, it's consisting of protons, the positive charges. In between protons here and there, the neutrons are there. So how come these neutrons and protons are put together to form a nucleus? So what is the gravity between them? How much the gravity is changing between them from point to point? So if you know exactly what is the gravity or the attraction which keeps things together, just like a nucleus, okay, if you understand better, you will have you can plan something, you can come up with a new advancements when it comes to fundamental physics. Okay, so you have to measure the forces of attraction, the gravity kind of a things at even the quantum level, the atomic level as well. Okay, and starting from the real world scenario to atomic scenario, there is something called astronomical level where somebody wants to ascend a ship, spaceship beyond solar system or at least beyond our Earth orbit. In that case, we will be doing some space missions. There, you will not be able to rely on some satellite which will locate the object or a spaceship. In that case, the spaceship has to rely on the gravity it faces from the surrounding planets. So that is where, if it can map the gravity exactly, it can navigate in a particular direction. Okay, so looking at these scenarios of right from the atomic to real world scenarios, that is macroscopic scenarios and beyond astronomical level, there is a reason, there is a need for measuring the gravity exactly to a certain precision. So that is where this gradiometry is going to come into play. Okay, and why is that so here? If by nature, if you see, gravitational force of attraction is by like very weak by nature, it requires a extreme precision. Okay, it varies from point to point. But when I let's say if I'm standing at some point on the ground floor, if I go to the higher floor, I may not feel that difference, the weight difference. If I measure my weight at the ground floor with some weighing balance, the weight would remain the same at the top level, top floor. But if I have a weighing balance to a very good accuracy, let's say fifth and sixth significant figures, in that case, there may be a variation in the gravity that is changing with respect to the z-axis, means away from the center of the earth. Okay, how much it changes with an altitude, if I know, I can exactly locate an object depending on the variation of this gravity with respect to altitude. Okay, so let me go further. So to do that, people were earlier doing something kind of classical gravimeters. Okay, so basically it's consisting of some kind of a spring and some kind of a soft silk, and there's okay, some sensors, capacity sensor, some locking pendulum. Okay, so pendulum unit, and there will be some kind of a oscillatory phenomena is measured right, to a very good accuracy. Based on the oscillations, you will find out what is the gravity in that particular location. Okay, as you know, if I just take a simple pendulum, if I just take a pendulum, okay, if it's made to oscillate, it is going to have at extreme points going to have, okay, it's at the extreme points it will achieve maximum potential energy, max potential energy. At the center it is going to reach zero potential energy, but it will have maximum kinetic energy at the center. Again it will reach to the right extreme, it will reach a maximum potential energy. At the same time it reaches the zero kinetic energy. Okay, so basically what happens is the potential energy and kinetic energy exchange the values between them. If I plot potential energy versus kinetic energy, sorry, potential energy versus time, it will be something like this. On the other case, right, kinetic energy is something exactly opposite. Okay, right, at some point, I'm sorry, this is something of different. Whenever kinetic energy is maximum, potential energy is minimum, something of that sort you have to understand. Okay, right. So now the question is, okay, what is the oscillation frequency? If you find the oscillation frequency, or omega per se, it is equal to square root of L by G, length and gravity. Okay, right. So depending on the frequency, you can find what is the gravity. Okay. Similarly, you will find the gravity to act greater accurate value depending on the oscillational frequency. Okay. But when it comes to classical gravimeters, there is some issue. Just now we saw it's made up of mechanical system. There is a mechanical drift, maybe due to some wear and tear. Probably there is a mechanical drift, variation in the values as time progresses. Okay, right, and there is a thermal noise. Sometimes the mechanical device do after some due to some friction, they generate some noise that may fiddle with the accuracy values. Okay, and which means whenever I reuse the device, I need some accurate some kind of a calibration I had to do, right? Some calibration, for example, how do we calibrate given weighing balance, whether it's working or not. So we will have a ready, like some kind of a weight, some kind of a weight, which is precise weight. Let's say I want to check why my weighing balance is working fine. I'll have a weight of 1 kilogram weight. I'll put it and I will see whether it is exactly showing 1 kilogram or not, the weighing balance. So that kind of a cross check I have to always do due to this issues with the classical gravimeters. Okay, and suppose just now we saw it's an oscillation, right? It has to be not disturbed by the surrounding vibrations. Let's say the measurement tool is put somewhere, there is a vibrations below, that vibrations go and influence the actual oscillations being taking place inside the device. So there is a sensitivity to the external vibrations. Okay, so that is a problem with the external classical gravimeters. Okay, so that is where people thought, can't we use some kind of a quantum solutions there, quantum gravimeters. Okay, very good. So that is the place the quantum can come in. As we know, quantum systems are very sensitive. Okay, how sensitive? They're sensitive to a very great extent. As atoms and photons are involved, when it comes to atoms, they easily excite to a higher order when I influence with some ambient temperature when I consider an atom, which means the atoms are seriously sensitive. Our electrons inside an orbit are seriously sensitive. So, based on that, people thought, why can't we create some kind of a measuring tool where I can measure a gravity, effect of gravity in the atoms. Okay, even though atoms are very small, yes, there is some kind of an effect on the gravity because the atoms do consist of some weight. So I will talk in terms of not single atoms, a bunch of atoms. So a bunch of atoms, when I put into some gravitational pull, how are they going to behave? Depending on them, we are going to measure the gravity. So this is an interesting scenario. If I use this, it's a quantum solution. It can overcome mechanical drift. It can be drift free, because I'm not going to rely on some mechanical rotator or a pulley or something which measures the frequency of oscillations. Okay, and it can be SI traceable. It can fix, right? Okay, exactly specify some kind of a SI unit for measuring. Okay, and since there is no mechanical part, atomic parts are involved, what we can do, you can avoid the long-term calibration. I don't need to calibrate. I can straight away use the device. Since if you alienate, separate the system, avoid the system not to interact with the surrounding, means enclose the system perfectly. And in that case, you can use something called atomic reference. Okay, means atomic transitions you can use. Based on the transitions, you can measure the gravity to a very good accurate values. So that is the alternate for the classical gravimeters challenges. So let me go further and see how it is possible. Okay, right. So there is matter waves, the de Broglie hypothesis mentioned here. Let me tell what it is. Okay, all right. I was talking about this from quite some time earlier also, but nevertheless, it's worth discussing. Let's talk once again. Okay, right? So let me use my board here. If there is any question so far, please put it up on the chart. We can definitely discuss on that. Okay, so far no questions. Let's say if I just take a double slit experiment, if I just take a double slit experiment, what is a double slit experiment? Okay. Okay. Probably I might, yeah, yeah, I can use my, okay, let's take a coherent light source, coherent laser, coherent light source. It emits a stream of photons for sure. Then I'll take some kind of a double slit setup where there is a slit one, there is a slit two. Basically, some kind of a opaque material, means not a transparent, but there is a two small holes are there. Through the holes, what happens? The rays can penetrate because it's a holes. So now what happens? Through S1, the rays will come out once again. Through S2 again, rays will come out once again. Now if you see S1, S2, they themselves could act like a sources of their own. Only thing is they're generated from same current light source. Okay. Now, on the other side, let me say there is a screen. Let me take a screen. Let me do this experiment. Now, a bunch of photons are the rays of electromagnetic wave in the coherent form. What is a coherent for me? If I just take a rays of this light source, they remain to be in nice sync continuously. Wherever the first ray peaks in same position, second ray also peaks. If there is any difference between the peaks, that difference time would be maintained as long as time progress. That is what the phase difference is, fixed phase difference is maintained, or a fixed path difference is maintained as long as rays travel together. This is how the current light source is actually manufactured or designed in the first place. Okay. Now, if I have this rays coming out from S1 and S2, let's say take a location where what happens? One ray from S1 comes and goes and hits. Similarly, another ray from S2 will come and hits exactly in phase. What I mean is they exactly in same phase, in phase they hit. What happens? They increase the location, the intensity. So what you see, some kind of a bright fringe you see, right? So it's some kind of a constructive interference. Constructive interfere. Light rays interfere constructively and creates a bright fringe. Very nice. At some other location, let's take another location where Light from here comes and hits this at some phase, and the light from the S2 will come exactly hits in opposite phase. When it hits in opposite phase, what happens? A dark fringe is created. Means dark. It's a destructive interference. Okay. So because of this, what happening is light which is supposed to be there here redistribute somewhere, it goes to acquire somewhere else. Basically, interference is nothing but distribution of the light at different points. There is some constructive interference, there is a brightness, there is a destructive, there is a darkness. Now it is obvious to see because light is travels like a waves. Okay. So if I draw wavefront for S1, it comes like this. Wavefront. Similarly for S2, if it comes like this. So the wavefronts themselves would interfere constructively and destructively. Whenever they interfere constructively, the wavefronts, I get a bright fringe. Whenever they interfere destructively, they'll get a dark fringe, the wavefronts. It is obvious to understand. We know that the light rays are like that. Okay. The simplest another classical analogy I can give is suppose let's say I have a rope is tied here between two points. Let's say some point somebody creates a wiggle means some disturbance. So if you create a disturbance travels and it's to the other point and then it comes back. Let's say disturbance is happening. Okay, so it was created at this point. Let's say somebody tries to disturb it a point where a node is there. If I try to disturb, what happens? The wave completely just gets destroyed. So if you are in sync, if you try to pull exactly here, you are giving an external force in sync, in resonance, the wave would sustain for a longer time. That's what we are doing, continuously giving oscillation. So if you are giving oscillations, the vibrations at one point, continuously you see the vibrations. If not, if you give completely opposite, the waves will die out. So that is what the destructive interference for you. Okay, right? So that is understood. The waves are having such a feature. Now, what people thought, okay, waves behaves like this, very good. Now, instead of having a coherent light source, let me do the same experiment. Okay, this time with some kind of a electron gun. Take S1, S2. Instead of laser source, let's take an electron gun. Electron gun, which is actually based on some photoelectric effect. Probably what it does, there's a metallic film is there. You continuously strike the metallic film with some kind of a photons so that electrons are ejected. So basically what I'm saying, a bunch of electrons, a stream of electrons are continuously ejected, just like a stream of light. Okay. Now they were ejected in the direction of S1 and S2. Okay. So something of that sort. Now, let's say I have a screen on the other side. What our intuition says is we usually think the electrons will exit through S1. Probably it will go and hit at one point and start accumulating at the same location. This is what our intuition says because for us, electrons are material objects. So that's what we see. The electrons from S2 will go and hit to the location where it's a straight line, so they go and accumulate. This is what we think. So bunch of electrons accumulate at one point due to S1 electrons, and some more through S2 will accumulate. This is what we usually think in the real world scenario, macroscope world scenario. But in fact, if you do this experiment, what you see is not this one. What you are going to see is, okay, let me remove this. What you are going to see, interestingly, on the screen, there is a locations electrons are accumulated. Okay, there is a location electrons are nowhere accumulated. There is a location electrons are again accumulated. So basically, it's like a fringe of electrons wherever is. If I do this experiment like earlier, if I do the experiments with the light, wherever there is a bright fringe is formed, something very close to that, there is a accumulation of electron. Let me call electrons being there, I will call it the bright. Wherever there is no electron, I'll call it a dark. Okay. So which means electrons accumulating just like a fringes, similar to electromagnetic radiation, which is behaving like a wave. So it was one of the confirmation showing that the light, like matter waves, like electron waves, do behave like a, sorry, electrons, the stream of electrons behave like a wave, which means electrons travel like a wave front from S1 and travel like a wave front from S2. Wherever there is a constructive interference, they accumulate. Wherever the destructive interference, something like they may collide, they get redistribute. Redistribute, they will not accumulate at some point. So this is a confirmation that yes, electrons by nature very small do behave like a wave. They are not waves. I can say there is some kind of a wave nature get associated with them. Due to that wave nature, they are going to show some kind of an interference pattern of constructive and destructive interference, which confirms that, okay, matter waves are exist when it comes to quantum level only. Because you can ask me a question, why not at a larger level? Why not matter waves doesn't exist at a larger level? Let's say real world scenario. Let's say if I have a bullet, if there is a gun, conventional gun, okay, a bullet is fired, okay. Now, bullet is a small quantity, travels with a very good speed. The mass of the bullet is something like few kilograms, let's say 100 into 10 to the power of 100 kilograms, let's say 10 to the power of minus 30, sorry, minus 3 kilograms, 100 grams means it can travel with a velocity something like 100 meter per second, roughly. So then, De Broglie said there will be association of wave for any particle which is moving. If it has a mass, then you can find its corresponding wavelength of wave nature, which is directly equal to Planck's constant divided by mass into velocity. By the way, Planck's constant is order of 10 to the power of minus 34. If the mass of the object here is 10 to the power of minus 1 kilogram, velocity is 10 to the power of 2 into 2 to 10 to the power of 2 meter per second. If you try to find what is thus wavelength, which is 10 to the power of something like minus 35 or more, 10 to the power of minus 36. So, okay, so which means very, very small wavelength. I cannot measure this wavelength at all. So I can simply say the wavelength or wave nature associated with a traveling bullet is negligible. You cannot measure it. But when it comes to traveling electrons, a Planck's constant is 10 to the power of minus 34. Mass of the electron is roughly saying 10 to the power of minus 35 kilograms. It can travel close to the velocity of the light, 10 to the power of 8 meter per second. If you find the wavelength, which comes out to be something like 10 to the power of minus 10 meters, which is about 1 angstrom, okay, which is very close to the optical frequency, the light frequency or light wavelength, we can see and measure. So that is where I would say the light or the wave associated with these particles like electron is measurable. That is why we can see them. We can use some advanced tools to measure its wave nature. So that is where we will say, yes, matter waves exist at a very tiny level. Electrons and atoms are molecules. If I make some atomic gas, if I make atomic gas to travel through some space, I do have some kind of a wave nature. So I do have some kind of a wave patterns in that. Okay. So that is a confirmation. De Broglie has given, Young's double slit experiment has confirmed. So here you will see H. Sometimes people write H cat. Maybe I should not write H cat. Here I was writing. Please excuse me. So simply I'll write H. Okay. So fine, let me get back to the PPT here. I would say matter waves and de Broglie hypothesis is atom behave as a coherent waves at ultra low temperatures. Why ultra low temperatures? As you know, at the ambient temperatures, electrons can be knocked out of the atom and nuclei probably they are stubborn, the electrons goes uncontrollably. I want to have a control. and I want to keep things in my control as the temperature induces a lot of disturbances. So that is where I'm going to use ultra low temperatures. So best possibly, I'll take an atomic gas, I have to cool it to a certain extent where atoms do stay in the a particular some particular I would say vision particular location. Okay, so for that, what people did, probably people use laser cooling, which can allow one to extract the energy out of the atoms to such a level the entire system can drop to few nanokelvin. That is a very very low temperature. Okay, once that is done, we can expect some kind of a coherence, like some kind of a synchronicity in the behavior of the atoms to exist. What kind of a coherence? Exactly, okay, wait a minute, exactly similar to what we had in the case of laser light. You see, nice coherence, right? The flow of rays have a nice coherence. Similarly, when it comes to electrons, if I cool it to low level, they do possess some kind of a coherence. Means coherence length means within a certain length, if I consider a certain number of in the volume, if I consider a bunch of atoms, they behave in a same fashion. Okay, that is what the coherence for me. Okay, so they all are alike. I can represent them all by one quantum state. I will say they are all in the pure state, quantum pure state when it comes to their quantum superposition state. Okay, so that is a coherence state for me, so which is possible by laser cooling. Okay, so what people thought, oh, very good. The moment I have such a thing, coherence lengths, can I make them to interfere? I can make like light rays to interact with each other. Similarly, can I make light ray like a waves out of atoms or atomic waves to interfere? Yeah, that's what the idea. So this is some kind of a AI generated figure which gives the essence for us. What is that essence is? Let's say I have a stream of atoms are here. Okay. What we are going to do? We are going to incident a pulse in such a way, right? A pulse will disturb a bunch of atoms which were together keeping quiet because they are all made into exist in the same quantum state. Let's say the pure state. Now what happens is a bunch of pulses will come and disturb that. What is the disturbance is? It's like there is a police, there's a group in the city. Sometimes the police comes and disturbs and deviates the people. So in the same way, the photons incident pulse makes a bunch of atoms to flow in one direction, another one in another direction. Let's say there's two streams of photons were traveled. Okay, when let's say they're traveling, so they're traveling in space. Okay, when they're traveling in space, you see there some of them is at a higher level, some of them at lower level, right? They have a mass, you see. Because of the mass, what happens? They feel some kind of a gravity. The lower ones feel certain amount of gravity, top ones feel certain amount of gravity. I'm talking in terms of microscopic level. Few atoms together may feel some gravity. Now, the ones which are traveling at the bottom will may feel a little less gravity. The ones which are at the top may feel a little more gravity. There is a small change in the gravity due to this altitude, z altitude. Now, what happens? I will send another pulse in such a way. Okay, the photons, sorry, electron atoms which are traveling were made to deviate from their actual path so that they will take a deviation into some direction. In which direction? Let's say I have one pulse from the top and one pulse from the bottom, which acts on both the atomic beams, which were made to interact at some point, right? This is just like Young's double slit experiment. It is just like the interferometer. Okay, so in the interferometer, what you see, right? Let me give the interferometer picture. So you will take a light from a coherent source, you take a beam splitter, PS. So a part of it reflected, a part of this goes through. The ones which goes through, I'll take a reflector there. So the light gets reflected. I'll take one more reflector. So again, light gets reflected. Okay, right? How long I'll take a reflection is, I'll take a reflection such a way, right? Light comes and hits and exactly goes through this beam splitter. Okay. Now you will say a part of light, let's say there is a path 1, there is a path 2. So path 2 means the light has to go through one extra ring and then it interact. Okay. So path 1 light is just exit. So at any given point, if say path 1, okay, and path 2 means the light previously came, that will make one ring and comes and interact with this beam splitter. What happens? This is the location, the interaction of two two rays of different light traveling direction. Okay, right? So there will definitely, if I have a coherent light source, if I try to make same rays with the same fixed path difference or a phase difference, I might not see any effect. But if I have a extra path created to an extra ring, now by any means the path length, let's say P2 gets affected by let's say I'll have this mirrors fixed. Okay, this beam splitter, let's say it moves back and forth due to some gravity as due to y. Let's say I'll keep this beam splitter on some kind of a device which moves back and forth. Okay, how accurately I have to measure this beam splitter motion back and forth, which can be found from the interference pattern fringes, bright and dark fringes, which I see here. How far the fringes are located, what is the width of the fringe. Depending on that, I can find what is the path difference these two rays are actually experienced when they interfere. Depending on that, I can find accurately what is the location of this beam splitter. Or this is Michelson interferometer. This is how people are going to find some the motion of let's say light coming from the sun, the motion of the earth with respect to sun. Okay, all right. So this is a technique where the small changes can be measured in terms of interference pattern. Okay, right? So the same idea which we can use here. What is that idea? Is we can make the this two rays which were split, sorry, two atomic rays which were split, made to interact. So this is the interaction point. Once they interact, okay, and you can, okay, so we can make them interact. If you try to see the interaction pattern, okay, you can see the interaction pattern in terms of some fringes, just like the fringes which we saw in the case of light. So probably if the presence of atoms at some location, no atoms in the another location, just like a wave function showing, okay, some kind of a pattern. Similarly, a wave function associated with this atoms could be seen, and that wave function will predict or exactly give the probability distribution of the atom at some location, no atoms at another location. Now, depending on the fringe pattern, we can measure, okay, what was the effect of gravity and the top one, because the top one having more gravity, the lower one is having less gravity. So how much gravity is being varied dg by gs as the height where goes. Okay, if I want a better accuracy, probably I'll deviate to a longer distance and then make them to interact. So for this, we use something called a pi by 2 pulse, the beam splitter. Okay, I'll take 5 by 2 pulse. For example, I want to, let's say some ray is going, I want to reflect completely backwards. I want to induce a pi by pi pulse, a pi phase. So over that, it's something which is traveling in a positive direction has to become a negative. So I'll induce exponential I pi, so which is done by pi pulse. That is what a mirror is being created out of a pulse of rays. Okay, and when it comes to quantum computing, if I have a quantum system, pure system, if it is goes through a Hadamard gate, it becomes superposition of 0 plus 1, like an equal superposition. Okay, so the Hadamard gate is like a beam splitter. When it comes to when it comes to some kind of a pulse, I can split the atomic waves into two parts using such a Hadamard gate. Here in this case, a pulse. So what kind of pulse is that? It's a 5 by 2 pulse. In the block sphere representation, if you see, okay, initially, if the atoms are represented along the North Pole, 0 ket. If I act a Hadamard gate on the 0 ket, what happens? It creates a superposition state of 0 ket and 1 ket, which is along the x-axis. So what happened? This is a plus ket. What is that happened is the rotation of 0 ket about the some y-axis. Okay, so the pi by 2 angle it is rotated. So that's why it's called pi by 2 pulse. So you can use that analogy to understand. So basically, I'm going to create an interference between a matter waves and see how much interference pattern is being changed with respect to, okay, as I increase the wave, the distance between the atomic rays which are deviated, probably there is a large variation in the gravity from the top hand to lower hand. So in that way, we can measure it. Okay, so this is some kind of a more elaborative way you can understand. Okay, so let's say a stream of light, sorry, stream of atomic vapor is coming in the state of 1. Okay, right, with some polarization, with a propagation vector I can associate with the polarization. Let's say I use some pi by 2 pulse, and from the both sides, you see, so that I split the pulse, the atomic vapor, into two parts. One is traveling straight without being deviated, other one is slightly deviated. Okay, so the first one remains with the same polarization, but the one which is deviated will acquire the change in the polarization direction, which is represented by some P plus H into K effective. Okay, so K effective is something to do with the propagation vector of the light, which I introduced K1 and K2 here, which together is going to induce some K effective on the atomic vapor which is traveling. Okay, now I will let them travel in the deviated direction. One just travels like this. Next time I will add a pulse so that I want to deviate the the one which is not deviated made to deviate, the one which is already deviated made to deviate in a little bit a different direction, so that it acquires the same old polarization state. Basically, making them to first I'll diverge them, later I'll make them to come together. So what is the purpose of diverging means one of them acquires some extra gravitational pull on them, the other one have same gravitational. Okay, so in this way, what you see, the first half the part of the atomic vapor travels as it is, but second half, which was acquired some extra polarization, later was made to go and fall in the same polarization direction. But what happened is there is a path difference, extra path they traveled. Okay, now, so basically, when they're made to interact by using another pulse, pi by 2 pulse, when they're made to interact, this is the place where they interact. When they interact, I'm going to see some kind of a fringes. What fringes? Presence of atoms at one point, presence of atoms at some other point. Okay, so that is another analogy picture is given on the right. You see, so bunch of atoms are taken and they are split into two bunches. Okay, depending on their path, their polarization, they may to appear to be different colors. So initial polarization was maintained for the first half. For the second half, different polarization is acquired. Another mirror deviate, like a mirror polarization is incident light is done. That will make them to interact. Now see, according to the path they have taken, the polarization was made to change, and they were interacting at some point and they will just come out. While coming out, we'll just notice where the redistribution of atoms are happening. From there, I can make out what was the effect on one of the stream. On the top stream, what was the effect of the gravity? So the schematic diagram is given at the bottom. So there is a beams, there is a Raman power monitor, and there is atom detection. So from there we can see location wise where the atoms are located. The dimensions is very very small, 163 nanometers. Okay. On the right, it is given the actual downward Raman beam, and laser cooling beam is also given. So this equipment is done with some laser printed. So I have a reference given at the end for this PPT. You can go through it in detail. So the idea is to create an atomic interference. Once I do it, what can be achieved? You say, okay. So there is a effective propagation vector was achieved by any stream of photons when it is stream of atoms when it is exposed to two kind of light rays. One is K1 propagation, another is K2 propagation. What was the effective propagation they will achieve? K effective. Okay. So in general, the phase difference of the coming out light is directly proportional to the K effective and acceleration due to gravity. And what was the time lapse between the rays which I have chosen? For example, here I say, right, I choose the time lapse between each of them is some time t, some periodic way I will do that. So that is connected. Okay. Now if we say this is the pad, this is the map, this is the quantity I can measure, acquire from the fringe pattern, the light fringe pattern or the interference pattern. Okay. So once I measure the stream of atoms located, I know delta f, delta phi. Okay. K effective I know. Okay. Due from the incident pulses, T I know I can easily calculate what is the acceleration due to gravity. How effectively I can calculate is depending on how much deviation I can create. If I create a lot of deviation, I have a very good effect of gravity. I can find out exact value even at the later significant figures. Okay. So this is the core sensing mechanism when it comes to gravimetry. And the question is, what is a quantum in it? The quantumness in it is coming from creating a beam, a pulse of photons creating a beam splitting of atoms, okay, and then combining them, making them to interact, making them to show some kind of a quantum interference, and from the interference pattern making out the exact gravity values. That is actually the quantum sensing. Okay. Now the exact experimental setup, what it would look like, it will going to have ultra high vacuum chamber, and you need to trap the atomic wave. For that, you may use magneto-optical trap. So there will be a magnetic fields apply from the top to bottom, and also you use some kind of a bunch of optical uh, optical beams to trap the atoms in that. Not only trap in one location, you can trap them in kind of some kind of a grooves created. So right, so there is a magnetic traps and there is optical traps. Together you can trap them, and after that you incident the light from a pi by 2 pulse, pi pulse, and then pi by 2 pulse in the sequence of time. Okay. So once you start applying, say here, if it's given at the application time initially, and later time, and then later time. Okay. So the first, when you apply, you will split into two parts, and then they will made to exist, and okay, at different heights, and they're actually made to fall through the uh, uh, height. Okay. Only particular one half will be up, one half will be down, and later they were, after traveling certain distance, they were made to interact. When they're made to interact, okay, and they will interfere and they evolve as some kind of a fringes, so that you can measure at the bottom. Okay. Or using some kind of a detector. Okay. Or you can measure from the top. some seismometer. Okay, so what you are going to see, you are going to see vibration isolation platform, and so this experiment would let you to calculate the fringe pattern, and from the fringe pattern you will exactly get what is the gravity. Okay, right? So fine. So you are going to read out accumulation of atoms at one location. Let's say electrons, if I do the experiment with electron, so some kind of a population readout. Okay. So at some location, depending on the, the path phase difference they experience the atoms, I'll see some kind of a population accumulation. So you are going to measure in terms of fluorescence detection. What you do at some location, you incident a light. If there are atoms there, they excite and they re-emit. That fluorescence you detect. If there is no fluorescence, there is no accumulation of atoms. So this is what the fringe pattern analysis. So from the fringe pattern, how far the fringes are, that is measured with the delta phi. So from there you can get exact values. Okay, right? So when it comes to absolute quantum gravimeters, what can be done? Okay, advantages is drift free. You can make a perfect SI traceable units. Okay, and no mechanical springs here. Okay, only atomic transitions defines the change in the state of the system. Okay, and atomic transitions would be get affected by the gravity also. Okay, and the who actually doing research in this field, the Stanford University and UK Birmingham University and Imperial College London and NASA and other places, these people are being using mainly when it comes to find the gravity to an accurate level. What level? The precision up to 10 to the power of minus 9, right? So which means up to 9 to 10 significant figures they want to measure the gravity. Okay, fine. So the concept here, gravity gradient concept, variation of the gravity as the height changes. Okay, right? Instead of measuring absolute gravity, you can measure the spatial gradient. So for that, if you made some system to exist some height and another half exist later height, when they made to interact later, because of their presence at different altitudes, they might have had like signature of gravity acted upon them due to the position change. So that you can acquire from their interaction pattern. So the gravity, the gradient is extracted from the interaction and the evolution of the system. For that, people even thought about something called dual atom interferometers. So what is that is two clouds are two atomic clouds are separated by some baseline length L. Okay, right? So once they're separated and they may feel different gravity values. Okay, and after some time when this made to interact, they're going to show up. Okay, some kind of a vibration cancellation between them, just like constructive and destructive interference, what we see in the case of light. Okay, from there, differential measurements, right? We can measure exact gravity values. Right? So this is a schematic picture on the right, and the exact picture, if you want to see, it is there on the right side. Okay, so upper atomic source I have, lower atomic source we have. Okay, a region of interest at the top for precision atomic interferometry, and there is a baseline separation. Okay, so they are separated to a certain distance, so that the top one feels a different gravity, lower one feels a different gravity. Okay, after some time they made to interact. At that point, they will evolve due to their different environments which they have faced in the initial stage. Okay, so this is a differential phase measurement. So this is the gradient, the gravity gradient. Now earlier we didn't have a L dependency. This time we have a L dependency coming into the picture. Earlier we have just G. Now it is replaced by dG by dL. Okay, fine. So now we can exactly measure what is the variation of the gravity as we go to change atomic level, very nanoscale level change altitude. We see exact change in the gravity. Okay, so yeah, right. Sensitivity limits. How much sensitivity limits I can achieve with this kind of methods is depending on number of attempts I make. Okay, for example, if I make a lot of attempts, I can reduce the error. Okay, short noise. How much noise I can acquire? Okay, in a given calculation, given attempt would be reduced by making more number of attempts. Okay, and even some people given thought about, since we are talking about creating a split of atomic vapor, if you can make them entangled, there is something called spontaneous down conversion, spontaneous down conversion. What this process is in the light case, if you just take a coherent light source, let's say it's consisting of photons of 100 joules. If I make them to go through a nonlinear crystal, okay, nonlinear crystal, let's say 3-level atomic system it has, okay, the crystal is of a capacity such a way, okay, let me draw this very close to each other. Okay, so let's say the separation of this first to last level is say 100 joules. Okay, now what I can make is I can make the electrons in the ground state to excite all the way to excited state, and once they're in the excited state, while coming down I can make the de-excitation state, the excitation such a way for some time, for a moment of time, electrons stop and they emit 50 joules. Later also they emit 50 joules. Basically, what I see, 100 joule is got split into two 50 joule photons. Now, since they are coming from same kind of a stream through nonlinear crystal, okay, nonlinear crystal, what I can make some kind of a correlation between their polarization. What kind of a polarization? I can make a polarization in such a way it can be an entangled polarization. What is entangled polarization is, let's say downward, oh, vertical plus horizontal divided by square root of 2. This is the entangled state. The first one is a top beam, second one is bottom, top and bottom. So it's entangled. The photons on the top are entangled with bottom ones. So this is how you are going to create entanglement between a bunch of photons coming from coherent light source. So this was the idea. Can we use this idea when it comes to the distribution of atomic vapor, which we had in the case of graduatory? Of course, there is a possibility, since we are talking in terms of a split of atomic vapor which are traveling with some phase, right? So in that case, yes, we can create, this is talking about quantum states, I can have an entanglement between this stream of atoms and this stream of photon, bottom and top one. So in that way we can bring in additional factor of correlation, quantum correlation, which is by nature entanglement. In that way I can enhance the calculation to a much more greater values. Okay, so the entangled states can approach Heisenberg limit, which is 1 by square root of 1 by just n. Okay, so square root of n improvement I can achieve by doing this entanglement process. Okay, so noise source in this particular scenario would be many things. There is a seismic vibrations here, means the setup, and magnetic field fluctuation. The traps which you are using may have some kind of a magnetic fluctuations, may not work perfectly sometime, not to a greater accuracy. And laser phase noise, the lasers which you are maybe using to create a beam splitter and so on, they may have a noise. and Raman wavefront distortion. Okay, you may assume that the matching of mode locking in terms of propagation vector that may have some kind of a problem. So that is something to do with the nonlinear mixing of the waves that may have some problem. That may also induce some noise. There is something called atomic collisions. Atoms also collide. Okay, and so one has to do the experiment at a low density clouds. Okay, right? So we can use a beam profile optimizers, for example, to avoid the Raman wavefront distortion. Ultra stable cavities we can use for the laser matching, for the laser phase matching to reduce the noise. Okay, magnetic field fluctuations coming from outer environment can also be shielded with a mu metal shielding. Okay, magnetic fluctuations can be avoided. Okay, so in this way, the challenges are there, the sources of errors are there, which can be mitigated. So there is a research is being taken where non-Markov and noise modeling improves the phase estimation. So we address the noises as a non-Markovians and then try to mitigate them by some kind of a correction. Okay, so how much accuracy we can achieve? Like I said, 10 to the power of minus 9 G value. Right, when it comes to the dual atomic case, how much dent dg by dl I can achieve with respect to distance is something like 10 to the power of minus 12. Okay, right? So it is micro scale density changes which gives me that kind of a detectability. Okay, so like I said, applications is oils and mineral exploration. You can do a monitoring of volcano, and you can check for water bodies, exactly map water bodies. Under the tunnel, you want to travel through some kind of a navigation, you can do, and submarine navigation. And when it comes to civil engineering, you want to construct some kind of a bridges in the water body to connect across the water body. So for civil engineering, you want to say what is the strength of the surface, what are the waves, what is the effect of the waves, the water body, how far, how water travels through, all those scenarios can be captured and studied using this kind of a gravity effects. Okay, fine. So navigation without GPS is possible using gravimetry. As we rely on quantum, we can go drift-free inertial reference, works underwater, works in tunnel. Strategic defense importance it has. Okay, critical for GPS denied environments. Okay, so space-based gravitometry, there is something called gravity recovery and climate experiment, which is being undertaken by NASA from 2002 to 2017. There is something called gravity and ocean circulation explorer done by ESA from 2009 to 2013. Okay, so there are follow-up mission in 2018 to present from these entities. Okay, I have a references put up in this slide. The later slide you can check. So emerging compact systems also being explored, something like portable quantum gravimeters, or you can mount them in the trucks. Okay, and you can also make a chip scale level atomic traps, which can allow somebody to measure very fine, minute changes in the gravity. Okay, so the industry leaders are listed here. You can check them. So one is Qnami from Germany. Okay, so when it comes to research frontiers, you can use entangled atom interferometers. Okay, to enhance the accuracy, or you can go for hybrid A signal extraction from the output. Okay, and long baseline undercurrent detectors you can use, and quantum enhanced navigation, just like using the entanglement. Okay, so these are the research frontiers you can explore. Okay, you can immediately integrate with your research. For example, you are working on atomic interferometer simulations, you can do the quantum dynamics modeling by using this study. Okay, right, so there's so many frontiers, so many research directions which are listed here. I'm not going to the detail, you can use. So like I said, there are reference listed here. So the conclusion for the gradiometry is using a stream of atoms go and interact first diverge and they go on to interact later, and they show the effect of their travel in terms of gravity while they interact later stage. That is measured as an interference pattern, some kind of a population accumulation at later points. Okay, so that is what gradiometry is. We'll take a quick break and we'll come back at 4:20 and we'll talk about something called atomic magnetometers. Okay, so it's an extension of this one, and there we'll talk about in detail a few more things. Okay, so I'll stop at this point and we'll come back after 5 minutes. Okay.
Sure, sir. Sure.
Yeah.
Hello, Ashok sir, can you hear me?
Yes, sir. Yes, sir. We'll start. We'll start. Just a minute.
Sure, sir.
Yeah. I'm just. Looks like no questions.
Yes, sir, there are no questions till now.
Just give me a minute, sir.
Sure, sir, sure. No problem. So participants are encouraged to put questions in the chat box. Probably today is the last session in this QT-07 of Dr. Babu sir. So if you have any query, maybe in the previous sessions also, you can put your query in the chat box. Thank you.
Yeah. Welcome back, everyone. Okay. So we'll now discuss about atomic magnetometers. In fact, the gradiometries are actually a subset of these ones. Okay. So they've only addressed for gravity measurement. So we had put them separately. And as per the syllabus, we discussed them in first. And now we are discussing the broader sector of magnetometers, which are based on atoms. Okay. Probably you might have come across atomic clocks. In fact, atomic clocks, for example, cesium atomic clocks, were simply based on the number of excitations, okay, at a given in 1 second. Number of excitation is always fixed. If I expose a bunch of cesium atoms to external fields, they excite. So doesn't matter where you are, at what location, at what height or what position, it always remains the same. So people use that to measure a time duration, 1 second, how it is defined. Okay. Fine. Let me go further in terms of atomic magnetometers. What I have to convey here for you, okay, right? So again, why do we need to measure this? Some units, for example, here in this case, we are going to measure the magnetic fields, just like we earlier measured gravity, which is in a way some attraction, force of attraction between some objects which are going to have some mass. Here it is a magnetic force created by some kind of a magnetic entity on some small responsive entity. It's like a compass being influenced by large magnet. Okay, so we want to measure that magnetic fields at what level? Femtotesla. Okay, so why? For example, in the case of brain signals, which are at the range of 10 to 100 FT. Okay. So that means brain signals are so small, we need to measure them. For example, CT scan, MRI, all these things, which are actually based on how a human tissue is, or how human atoms or neurons or the contents of human body is going to respond to the external magnetic field. From there, they'll make out the structure of it. So, which is about 100 femtosla. And for example, MCG, for that usually people use for uh, understanding the heart. Okay, heart monitoring, right? Heartbeat and all, which is a CG scan, scan up to picotesla. So that is the range. So we need to measure that gravity, that for magnetic fields. Okay. When it comes to Earth magnetic field, so we can go up to 10 to the power of minus 6 Tesla. That much accuracy we need. We earlier we saw with the gradiometer 10 to the power of minus 9 range we want to go. But when it comes to Earth magnetic field, if 10 to the power of minus 6 changes minus 6, like up to 60 different figures, we know that is accurate enough. When it comes to quantum materials, okay, a material, how well it responds to the external magnetic field, at what level it will show change is even at 10 to the power of minus 9 test. A slight change at 10 to the power of minus 9 level, 9 is a significant figure. Even in that case also quantum materials change. They show change. For example, when it comes to quantum material means superposition states. The superposition state of a given system which is oscillating back and forth, that superposition would do respond to the external magnetic field. You know how? This the levels, the orbits actually get exposed to the magnetic field. They undergo some change. The orbits undergo change. That change is actually manifested in terms of the superposition change, superposition state change. That needs to be understood or measured. Okay, that is where the scientific importance comes in. Biomagnetism, medical diagnostics, dark matter search. People are searching for a dark matter in the here on the earth, which is exist at the astronomical level of space, or precision metrology for better material creation or finding a material. Okay, and quantum sensing evolution. Okay, using various ways sensing can be done accurately. For example, sensing hub, NQM sensing hub at IIT Mumbai, they use NV center sensing, so quantum sensing they do. So that is where the applications are lying. So we need to do that, we need to understand and we implement. Okay, so the key question here: how do atoms outperform superconductors without cryogenics? Okay, right? So earlier I had to eliminate the system, okay, in a classical, uh, uh, for example, classical magnetometers. So there probably I might rely on some cryogenics. So here in this case, atoms at microscopic level can be used to measure, right? So the magnetic fields, for example, NV center doesn't need any cooling whatsoever. Okay, so how NV centers can be used much accurately to measure a external magnetic field coming from, let's say, a human tissue which is having some cancer or not. Okay, right? So even the change in the gravity, it's like a magnetic field between cancerous tissue to healthy tissue is a very small level, 10 to the power of minus 6 to 10 to the power of minus 9 Tesla level. Even that could be easily measured when it comes to atom-based gravimeters. Okay, so look at the history if you see. So in 1938, it was proposed by Rabbi Isidore Isaac Rabi. What he proposed, molecular beam magnetoresonance. So this is the first precise atomic measurements. Okay, all right, which is done based on the atomic magnetometers. And later in 1946, okay, Felix Bloch, we use Bloch vector, right? So basically it talks about nuclear magnetic resonance. Nucleus has its own magnetic field which responds to the external magnetic field. So nucleus itself, if I just take a nucleus, it has some axis. It rotates about its own axis. Because of that, it has some magnetic movement. So that magnetic movement is thought like some small bar magnet. If I have some external magnetic field, let's say very large magnetic coil is there, it creates a magnetic field lines, something like that. Okay. So due to that field lines, okay, the nuclear magnetic resonance is created. Means nuclear magnetic alignment nucleus magnetic alignment may do a fluctuations, or it may precise on its own. Okay, instead of having pointing at a particular direction, it does the precision oscillatory, like kind of a rotation. So based on how it is precising, we can measure what is the external magnetic field strength, which is exposed, which is getting exposed to this particular nucleus. Okay, so which was done in 1956. Later, Norman Ramsey in 1949, they did precision spectroscopy. Okay, that's something to do with the transitions, atomic transitions, and using a separated oscillatory fields, it was given Nobel Prize in 1999. So this is also something to do with the transitions, atomic transitions, spectroscopy, in the sense you excite something, it de-excite. What is the de-excitation emitted field? Based on the de-excitation emitted field, we will assess what is this material is made up of. So that is a spectrometer for you, spectroscopy for you. And if I use an oscillatory field instead of steady state field, I will have certain different responses. So from there we can make out little more about the material as such. So that was a separated oscillatory fields spectroscopy. So in 1989 it was done. It was given a Nobel Prize. Sorry, 1949 it is done. It is given a Nobel Prize in 1989. Okay, that is based on the implications and applications. In 1896, Zeeman has given a very interesting effect. Actually, Zeeman splitting it is called. If you just take atomic spectral lines, which get split into multiple lines when I expose that atom to magnetic fields. This is in fact a base for atomic magnetometry. What I mean is, okay, if I have a consistent atomic or like conventional orbits, if I expose the system to a magnetic field, let's say there is a south pole, sorry, north pole, there is a south pole. So basically, magnetic field lines goes through this. The atom is there, ground state and the excited state. What happens, in fact, because of the field lines, the each orbit gets split into multiple orbits. Here, something like that. So just for convenience and understanding, I just showed you only two levels. Sometimes it splits to multiple levels. So we may call this is like a 0, 1, and this is 0, 2. And this may be called 1, 1, and this is called 1, 2. So for each level, it gets split into multiple levels. Now you see, initially, if there is electrons, if I put into the ground state, after the splitting, I never know. They may go to the ground almost, or they may go to the secondary ground. Okay, we know we don't have a control on that. Okay, depending on the situation, it happens. Okay, right? So what I'll do now, after exciting external magnetic field, there is a splitting happens. Now, let's say by any means, if there are no electrons in the lowest ground state. Now, if I expose this system to incident photons, which their energy exactly matches with this transition frequency. Let's say that is something with something of a color green light. Now there are no electrons which can absorb that kind of a green light because the transition frequency which matters. So I don't see the green light being absorbed, I just see emission of that green light. And let me say that green light exactly matches with this transition. Now you see, if there is a magnetic field, the electrons were put to the secondary ground state. Now the electrons in the secondary ground state, which cannot see this green light, which means the green light just ejected as it is. Let's say I switch off the magnetic field. In that case, what happens? The splitting is gone, electrons comes back to stay back in the old state. Now I incident the green light. Okay, and in that case what happens? The green light is absorbed. Okay, the green light is absorbed. and I don't see any transit, any light coming out. The system is absorbed. Let's say after some excitation, the electrons has to come down. While coming down, okay, I'll create some other state in between, or ensure that there is one more state, okay, where the electrons will come down and sits there, and I ensure that transition from in between state to the last state is forbidden. I can do that. If I do that, the light which emitted here would be of different color. If this is a green color, this is some kind of a red color, roughly saying. In that case, what happens? You see, light, green light is incident, electrons absorb, red light is emitted. From there, I say, yes, there are electrons in the ground state, they absorb and they emitted, they de-excite and they emit the red light. So this is in terms of Raman Stokes and anti-Stokes I described. Okay. Now let's say when I switch on the magnetic field, in that case, the green light is not absorbed, green light comes out, which means I can say whenever the presence of magnetic field is there, the incident light just comes out as it is. If there is a magnetic field is not there, green light is converted into red light. So just based on the light coming out from the interaction, I can make out whether the magnetic field is existing or not. So this is the one of the main recipe for NV center magnetometry, or per se for any magnetometry based on atoms. Okay, fine. Let's me get back to the presentation. Okay, so again, let's compare the classical and quantum magnetometers. Talking at the single entity level, let's say single qubit level, which is exposed to external magnetic field, how it responds. That is a quantum gravitometer for you. Or you take a bunch of atoms together, they exposed to the external magnetic field, just like nuclear magnetic resonance, MRI, or so CT scans here. In this case, what is the sensitivity which can achieve? That is a classical and quantum. So there is something called Hall sensors, Hall effect based sensors, where okay, a material is there, some kind of a solid state material. Okay, I'm talking about. Okay, so this is a material. I induce a current to left to right. Okay, now I apply a magnetic field from the top to bottom. Magnetic field. Now magnetic field is acting top to bottom, current is there in the right forward direction. Now if you see, if you apply magnetic field and current direction, you are going to create a Lorentz force on the moving charges. So the positive charges move to the one surface and negative charges to the other surface. Basically, on the surface which is towards us, probably positive charges accumulate. On the negative surface, on the other side, negative charges accumulate. Basically, you are creating kind of a capacitor. On the other side, there is a negative plate, and towards ours, there is a plate which is a positive plate, and there is a electric field is created because of this charge accumulation. This is called Hall voltage. How much Hall voltage is accumulated? You can take a voltage meter, you can measure that. Okay, so the moment you connect, you will see Hall voltage. Based on the voltage, how much is accumulated, you can measure applied magnetic field. So this is a Hall effect based sensor. Okay, so this is a classical setup where a combination of many charges effect is actually giving us a macroscopic effect. So in this case, up to what sensitivity I can go? Micro Tesla. Okay, do I need a cryogenics cooling? Probably no. And what is the cost? Reasonably low, very low, right? There is something called flux gate. Depending on the magnetic field, gates will respond. This magnetic flux, okay, the gates would respond. So there can go up to nanotesla. Again, they may not be needing any cryogenics, and the cost is reasonably low. Okay, we all know squid. Okay, right? Depending on the magnetic field, there is a change in the current and how much current is there. From there, we can measure magnetic field. Okay, so femto Tesla you can do, right? You see the increase micro to nano and then femto. And here, if you see, the squids do need a cooling up to 4 Kelvin. So the price is again, the cost is very high. So I want more. For example, I want to have more accuracy when it comes to magnetic field measurement. Okay, atomic magnetometers, like I said, NV centers, which can go less than few femto Tesla. Okay, right? And cryogenics is not needed, and the cost is, we say, moderate compared to the squid. Okay, so the key insight here in this case, atomic magnetometers achieve squid level sensitivity at room temperature by exploring quantum spin physics, making them ideal for portable and wearable applications. So something like people wear on their head, they can monitor the brain activity, okay, from the magnetic pulse coming from the brain. Okay. So coming back, the physics, like I said, atomic energy levels inside the magnetic field, how it responds. I was showing you the figure earlier. Due to magnetic fields, the atomic orbits split into multiple higher frequencies, like a fine orbits, little bit of fine orbits or fine levels, they will split. So that is what here shown in terms of an equation. Okay, how much splitting would happen for a given orbit or a given level is depends on applied magnetic field. Okay, so there are some Bohr magneton for individual atom. Okay, and magnetic quantum number corresponding to particular level, and external magnetic field strength also matters. Okay, and there is something called lambda z factor. This is atomic specific. What kind of atom I have chosen, for that it is going to have particular effect. So how much splitting, how given a single level is going to split with what difference delta E. Okay, how much delta E is can be done is given in terms of the applied field and the atomic parameters. Okay, right? So there is something called Larmor precisions. Okay, right? So for external magnetic field, the existing magnetic movement is going to precise. It is going to precise with some frequency. What is that frequency? How can I measure that frequency of thing is actually mentioned in Dharma precision. This is something called gyromagnetic ratio gamma. Okay, and the B is applied magnetic field. So we are going to get a Larmor frequency from there. Again, gamma is something with the material properties. Okay, right. So hyperfine structure for a ground level for rubidium atom you take, which is going to split with the, okay, 1 plus half. So one would be like a 3 by 2, another would be plus 3 by 2, another would be minus 3 by 2. So each F level, for example, here in the F level of rubidium is going to split into how many? 2F plus 1 sub levels. Okay. So splitting is measurable as a Larmor frequency. Okay. For example, a given atom may fluctuate between lower level to the higher levels, upper fun levels. So the fluctuation is measured in terms of a Larmor frequency. So basically, measuring Larmor frequency, you can measure applied magnetic field with a very good precision. Okay, fine. So there is something called optical pumping, means putting the system from atomic electrons from one level to other level through some optical fields. So you are going to create a spin polarization. Okay, so using circular polarized light. Okay, so just a minute. Yeah, sigma plus sigma minus photons that are positive, like a circular polarized, like a clockwise or anti-clockwise kind of a thing, which carry the angular momentum information in the units of Planck's constant. So they may be made to in interact with the system. So there I will be measuring the polarization of the system, okay, in terms of how it is rotating. From there, I can determine the possible transitions. Okay, so the transitions are not always okay. I can make only particular transition. So those particular transitions only I can induce. That can be created using a circular polarized light. Okay, right, there is something called selection rules in terms of physics, just like I was telling you earlier. The transition from the mid level to the last level I can avoid, like avoid direct excitation or de-excitation. So how it is done in terms of theory, it's called selection rules. In terms of experiment, I can choose the interacting fields with my atomic system in such a way such a de-excitation or excitation can be forbidden. So that is what the selection rules are. Okay. So here the transitions with delta m is equal to +1 only are allowed. Transitions means, for example, I have a level with a +3/2 and I have a level, let's say, -3/2. The transition is a difference of 3/2 minus of -3/2, that is 6/2. So that is a 3. Okay. So such transitions can be avoided. What transitions could be allowed? With a plus transition. So if, for example, if I happen to have the ground state is about 1/2. So here transition is possible because 3/2 minus 1/2 is 2/2, which is 2/2, which is equal to 1. So such transitions I can create. So among the split levels, I can create a transitions which are allowed. I can avoid such transitions which I don't want. In this way, I can select a light interaction with a split hyperfine levels. Okay. And we can also do a population redistribution. How? You have taken the electrons to go on to the level ground second level. Okay, so I can also choose the population to redistribute between the all the way ground all the way with the excited second first. Okay, this I can do, and I by using some fields, interacting fields, I can put the fields. For example, what I mean is, let me give you a picture. Let's say one level is split into two. Let's say another level is split into four. Okay, right? And I can make the existing electrons to go to the equally distributed states. Later on, I don't want anything here. So I can make them to go to the next state by putting a transition, sending a field. So I can push them here so that I will have the electrons, okay, redistributed like this. So no electrons in this state, I can do that. So in this way, I can redistribute the electrons in a given system, split system. Okay, that is what population redistribution is. And spin polarization based on the orientation of the magnetic spin that I can fix to particular direction by incident the field with a particular circular polarized light. Okay, so I can also create some kind of a dark state, means the atoms and goes and falls into the state, they may never see any external field. Okay, so it can trap. So that is what the dark states are, which is such a way is done it cannot see or any observe any particular light. For example, sigma plus, it's a clockwise clockwise circular polarized light. Okay, fine. So a specific block equations were to write down which dictates how magnetic resonance of a given spin particle influenced by applied magnetic field. If the magnetic resonance is resolved into x and y and z component, so how exactly that will respond to the applied field B, I can show in terms of block dynamics or block equations. So This will also encapture something called spin lattice relaxation and spin relaxation, means interaction between each spins. Okay. So basically, it encaptures how external magnetic field induces change in the system that can be measured in terms of variation of the system itself. Okay. So the sensitivity, quantum sensitivity limit, just like we saw earlier, okay, inverse of number of shots. Here in this case, it is also going to depend on the Larmor frequency gamma, okay, and as usual, some temperature, and yeah, so two to the coherence time, that longitudinal coherence time, okay, fine. Sorry, T is a time, and this is the ferromagnetic ratio, number of atoms. More atoms means more shots. Okay, more measurements. That way, you can have a better uh, external magnetic field accuracy. Okay, fine. So there are other magnetometers which we can talk. So let me quickly give NV center description. So we'll skip this the later application, since we want to talk in terms of quantum gravity. So the quantum gravimeters. Okay, let me quickly show you quantum sensing PDF. This one. Just a minute. Let me show you what I want. Okay. Just a minute. Single photon sensing. Okay, wait a minute. Take. Okay, atomic clocks I have. Yeah. Okay. I think somebody was talking earlier about NV centers. NV sensors magnetometry. So this is what if I have NV center. If I just take its atomic transitions are like this. Okay, atomic transitions are like this. Okay, when I have external magnetic field, the levels got split into, see, excited state split into three levels. The ground state is split into three levels. Now you see the redistribution of atoms happens. Now, if I incident a green light with 532 nanometers, in case if there are atoms in the ground state, then only you will see the absorption. And after absorption, there will be de-excitation and I'll see emission of red light. Okay. So the presence of ground state electron would tell me the presence of magnetic field or not. If there is no magnetic field, the green light never get absorbed. It comes as it is. From there also I can make out the presence of external magnetic field. So this is the technology. First of all, how can I get such transitions? So to get such transitions, what should I do? The technology of NV center. You take the diamond, remove a couple of carbons, put one nitrogen in it, and have one vacant carbon without being replaced by nitrogen, which is going to create a NV center, which is a dipole, by the way. Dipole in the sense of the negative charge separated by a positive charge. So it's a dipole. So this dipole is so sensitive, it will respond to the external magnetic field. So that external magnetic field is what showed here. So dipole transition, it can exist in two states, which is like 1E, 1A, right? In terms of magnetic field states, which when I have external magnetic field, like some tissue which is having some kind of a malignant part which has a different magnetic field. So that may induce such a superfine splitting. From the splitting, we can notice the presence of magnetic field. Okay, so this is about another kind of magnetometer which is being explored in depth at IIT Mumbai. So that's about a quantum magnetometer. So if you want more, definitely I'm going to share this slide PPT also, okay, as a state of the art quantum sensing. Okay, so today I am going to share three PPTs in addition to this one, so you people can explore. I have also added some references which you can explore. Okay, so so there is a question here in qubit simulation. How do we determine the exact rotation parameters required to prepare a measure an arbitrary quantum state? Okay, a very good question. So you are saying a quantum state is represented as a cos theta by 2, 0 cat, sine theta by 2, exponential I phi, 1 cat. When it comes to measurement, how are you going to measure a quantum state as theta comma phi? Okay. So basically, if you see, right, initially, let's say atoms are put in the ground state, means as per your block sphere representation, see, what is as per block sphere representation? Atoms which are pointing towards the north pole, atoms in the ground, not the excitation, at the ground state atoms, are in the state 0. Okay. Next thing is zero means theta equal to 0. Phi is not matters. On a single point, there is no phi. Okay. Next thing is I have to rotate that to x-axis, or let's say I want to rotate that to y-axis so that I'll have superposition state. Where let's say if I rotate towards the x-axis, the theta becomes pi by 2 and phi becomes 0. So along the x-axis, what is the state? The state along the x-axis, let me put a subscript, x which is equal to 1 by square root of 2 0 k plus 1 by square root of 2 1 k. So exponential I phi is 0. I am going to have 1 there. This is exponential I pi by 4. Sorry, sine theta. It's not exponential. So this is sine theta by 4 and also cos theta by 4, which is going to give me 1 by square root of 1 by square root. The question you asked is, how do we determine exact rotation parameters theta and phi? So how are we going to determine? It's very simple. I am going to send a pulse, okay, whose area of the pulse is what? Pi by 2. Okay. When I have a pi by 2 pulse, which goes and interacts with the atoms which are all in the ground, you know what that atom does? That pulse does, it puts the atom and the combination of into a combination of ground and excited. Sometime back, I think I did mention, let's say if I just take a single atom which is in the ground, if I send one single photon, it goes to excited state. It stays there for 1 microsecond. After 1 microsecond, I'll send one more photon. So the electron, after 1 microsecond, it tries to come down. I'll send one more photon. It goes back. So basically, I'll place 1 microsecond apart photons. So basically, that's the oscillation. So this photons together are called a pulse. What is that pulse? Is a pi by 2 pulse whose area is pi by 2. So the moment I make the collection of atoms to interact with pi by 2 pulse, which means I can expect the system to become a quantum superposition state, which is equally distributed between the ground and excited. Okay, so that is a pi by 2 pulse test for us. So the moment I have a pi by 2 pulse, which means the theta has become pi by 2 and phi has become 0 or any value between 0 to 2 pi. Because if you see, as per your block sphere, on the equatorial plane, any point on the circumference of equator is a equally superposition. So we can have various possible phi values still have equal superposition. For example, along the y-axis. What is along the y-axis quantum state? 0 k plus I into 1 k divided by square root of. This is also equal superposition. But what is the phi value here? Phi value here is 5 exponential. Okay, pi value is pi by 2. Okay. Likewise, I can have a specific preparation based on my incident pulse. What is the incident pulse? What is the area of the pulse? That dictates what kind of a theta and phi value the system has. Let's say the system is already prepared. How should I know in which state it is prepared? What is the corresponding theta and phi? What do I do now? I create one more qubit. It's like a readout qubit, test qubit that will go near to this qubit and extract that information without disturbing it. Or let's say I have a measurement tool, another pulse. Okay, what is a measurement tool? Measurement tool, for example, Z basis tool, MZ0, which would be represented as a matrix like this. MZ1 is a measurement tool represented like this one. If I bring this, act on this, it forces the system to fall with 1 by 2 probability amplitude into state 0, another 1 by 2 amplitude, it falls to 1. So it's basically, it is telling a system is prepared in equal superposition of ground and 0. Okay, so by using this, is also measurement tool is also pulse for me. Okay, so it's all playing with the pulse of photons interacting with the system. That is what people do with the coherent light source, that's a laser pulse. The emitted has to be detected using some kind of a detectors. Okay, so in this way, we can precisely do the experiments. Okay, fine. I hope I answered your question, Pankajaji, sorry. Thank you. Sir, I'm done here. I will
Yes, sir. So thank you very much for your time in this FDP. It was nice to hear you again, or like accepting our invitation for so many lectures. I hope participants have enjoyed the lectures, because you are doing wonderful, like is driving at everything, not only on PPT but continuously writing so many equations. I can appreciate, sir, your efforts for your talks. So once again, on behalf of participants as well on my personal behalf, sir, I thank you for your like active participation in this faculty development program. So we are coming to the end of 18th day today, and once again, thank you everyone for joining. Thank you, Asal sir. Bye.
Thank you, sir. So I am
Thank you.
immediately up.
Thank you. I would also like to extend the thanks to Ashwath Babu sir for his continuous efforts towards it and making these programs very learning and experiential learning programs. So thank you so much, sir.
Thank you so much,
Sir,
ma'am.
already taken 10 lectures in this course by him. So
Yeah. Yes.
25% of
Yes.
the whole course is covered by Dr. Ashwath sir, and with the same enthusiasm level from first to the 10th lecture.
Yeah.
It's very wonderful.
Thank you very much, sir. Thank you so much.
Thank you.
Thank you, sir. Bye, sir.
Bye, sir. I am immediately I have shared on the canvas the material which I used for the presentation, and I encourage people to just explore it.
Sure, sir.
Yeah. Thank you very
Yes,
much.
sir also makes us easy because sir himself upload the lectures PPTs in the Canvas portal.
Thank you, sir. Thank you.
Thank you.
Okay.
Thank you very much.
Okay. Okay. See you, everyone. Good luck with the entire follow